So, speaking of this, you just need to remember that when you draw displacement versus energy, it's like this. You have
Sir,
displacement, yes.
this will be what chapter?
Oscillation, the same, very long chapter. That's fine. Okay.
Hello, sir. Are you speaking? I can't
Okay.
hear you.
You can't hit what?
Sir, give me a second. I'll rejoin, all right?
Okay. Aman, you were in the AS class today. I think you were
Yeah,
there, right?
sir. Yeah, sir.
Okay. All right. Yeah, bad memory.
Sir, is x in centimeters or meters?
Okay, meters, sorry. Meters. And here you can write energy in joules. Okay, I think Javeria is back, probably. I don't know. All right.
Yes, sir. I can hear you now. Fine.
All right. Now, I just want to tell you that obviously there will be some maximum displacement in negative, and obviously the same maximum displacement positive. So the curve looks like this. Okay. So when energy is zero at maximum displacement, this means that this curve represents kinetic energy. When it shows you maximum energy on maximum displacement, it means this curve is the potential one. This is potential energy curve. And no matter what, some of these will give you total energy. Obviously, total energy curve is going to be constant throughout because total energy it cannot be created nor destroyed, right? So whatever the sum of energy at these points are, they're going to be the same, right? Is that clear? Hello, Mokshit, and hello, Ursulan. Okay.
Yes, sir.
Ahar, Nadia, latecomer still. Okay. Never mind. So if I were you, again, just to remind you, kinetic energy is half m omega square x naught square minus half m omega square x square. The first portion is total energy, half m omega square x naught square. And obviously the next portion is for the other one, which is this one, right? Very simple. Like I said, okay, now, so these questions are sometimes they do come like 40% chance from this chapter, which is a slim for all over the paper. But now, for example, this equation is given to you, and they show that the liquid column undergoes a simple harmonic motion. You're gonna write this equation. I don't know why my pen is writing so thick. Wait a second. And x, you're going to compare it minus omega square x, and you're going to say, okay, omega square is equal to 2g over L, like that. And that's very simple. and acceleration is directly proportional to the displacement. Now, so you might have noticed that usually, like the question we're doing since the very start, all of them basically have this sort of an equation where they give you an equation, they want you to, just compare them, and there's just kind of free marks, right? If you understand that. Anyway, now in this question, they say use the data to determine the length of the mercury column, and this is a 3-mark question. You see omega square is given by 2g over L. We can find omega by finding the time period. So there's 0, and here it is 0.5. It is in seconds. So it means that omega square is 2g over L. So we can write it as 2 pi over t, and whole square equals 2g over L. Now just add the values. So it's 4 pi square over 0.50 whole square equals to 2 times 9.81 and length. Can you please find the length? Yes, please.
0.12.
Okay. Everybody please check. 0.12 meters. All right. If Gatika is wrong, it means it's on you then. Okay. Then, so there's one cause of this damping. So if you look at this, it's basically like decreasing the energy slowly, right? So it's light damping. Do you guys understand this? With respect to light damping, you look at the diagram. What do you think would be the cause of damping here? Any ideas? What would be the resistive forces in this? There are two basically that I can see. No idea? That's not fair. All right, I'll tell you then. So first of all, the cause of damping could be number one, friction between walls and liquid. And you can also get away with writing air resistance because when it is moving, it's open. So air resistance might also cause it to slow down. Is that clear, everyone? Good. Now, it says total energy after 1.5 complete oscillation and total energy. Now, what is the formula for total energy? Anybody can please tell me? Yes,
So
please.
half m omega square x naught square.
X naught square.
X naught square. Okay, so we're looking at after 1.5 and half m omega square x naught 2 square. So you can just, you see this part and this part are common. So we can write x naught 1 square, x naught 2 square. Now, so after 1.5 oscillations, 1.5 means this is from 1, like 1. This is like one complete oscillation, right? This is another oscillation. Oh, we need to do 1 and 1.5. 1.5 would be somewhere, I think here, right? What do you guys say? So the displacement at this point is 1.1, 1.2, 1.3, minus 1.3, right? You guys agree? And the initial displacement was 2. So we're going to use that values here. 1.3 whole square over 2.0 whole square. What'd you get?
So we need not use the negative sign.
You can use it, but square would just cancel it. So it's not a big deal.
Okay.
Hello, Fahad. 0.4.
So 0.42.
0.42. Okay, very good. And there won't be any units because it's a ratio of the same quantity, so it will cancel out. All right, everybody understand this?
Sir, we could have left it at
Yes, sir.
0.4 though, right?
You could have
Because
left it at
it's, yeah,
0.4?
could we?
No,
Yeah.
no, that would
No,
not
because
be. Not
1.3.
0.43?
No, I'm saying because you said 1.3 over 2.
No. Basically, your significant figures in this are 2, right? So you have in your data, this is the data used, right?
Oh, right.
So
Okay, sir. Right.
in your data, there are 2 significant figures minimum. So it means either your answer could be 0.42 or maybe one more than that. Okay, but no less than that. Now, so this is, I don't know, this question basically came up again. The reason is that basically I give you this as homework, but I'm not interested in doing this because we have already done this. And I told you that the maximum values are not same and it's not a straight line. Okay, so you can write that. But basically what I'm more interested in is that you guys do it as homework. You need to complete this because this is a very similar question to the one we have just done. Okay, because they're going to ask you the same thing. They will ask you about the frequency, maximum acceleration, and then they're going to ask you about the energy loss. And you can obviously find the energy loss by finding the total energy from here, and then after whatever oscillations he has said, uh, after first 3 complete oscillations, so it's going to 1, 2, and 3. At this point, you're going to find this and subtract the 2 values. We took ratio above, we need to subtract to find the loss. Do you guys understand this?
Yes, sir.
Okay. So you're going to do this yourself. It's pretty easy, but I'm going to do this one. So this is the one that I'm looking for. So it says a student investigates the energy changes of mass oscillating to vertical spring as shown. And if you look at this is a displacement and energy graph, right? And if you notice, energy is given in millijoules, so that should be, considered very closely. What graph does this represent? Kinetic energy, total energy, or potential energy? Who's going to tell me this?
So kinetic.
It is kinetic energy. The reason I know this because when the maximum displacement is, the energy is 0. So that is only possible when it's kinetic energy, right? Now, state whether E represents oh my God. Why is he reading my brain? I don't know. But now you know why. All right, is that clear? Easy, right? So then it says the student repeats the investigation with a smaller amplitude. The maximum value of E is now found to be 1.8. Now, this is a very interesting question because right now, if you notice, this is 2.1, 2.2, 2.3, and 2.4. This energy is 2.4, right? Yes, Moksha. So this is 2.4, and the displacements are given here. And now they want you to basically determine the change in amplitude. Also, we need to show for this one, right? The issue with this one is that neither we have mass nor we have omega. We have nothing really. Okay, so what you're going to do? You're going to write that total energy is given by half m omega square x naught square. Do you agree?
Yeah.
Okay. Right now, we can say, and right now it is equal to 2.4 millijoules. Everybody agrees? Now, we can also write it as half m omega square. What is x naught? 1.5 whole square. Do you guys agree? Okay. Now, for the new one, the total energy now is half m omega squared. M stays the same, omega stays the same. I want to find this x naught when energy is 1.2 millijoules. What do you guys say? You get it? All right. Now think about it. Now, what you're going to do is just divide both equations. Make a ratio out of it. Okay. If I divide 1.8 with 2.4, what you gonna get? Half m omega square x naught square divided by half m omega square 1.5 whole square. Can I say that? Notice that this portion and this portion cancels out. So what you get? 1.8 times 1.5 whole square divided by 2.4 equals to x naught squared. Can you find x naught, please?
It's 1.3.
1.3? Okay. So it would be 1.3 and it's that simple. You guys understand now? So basically what we've learned is that whenever he's going to compare energies with respect to displacement, right? So you should remember that x naught 1 square or x naught 2 square will be equal to energy 1 over energy 2. And you can simply find it through this as well. This is very simple. Understood?
So don't we do the change in amplitude so it will be final minus the initial?
No, why?
Because the question asks for change in amplitude.
Oh, yeah, sorry. My bad. So it's 1.3, then 2 point, what was that? 1.5. I didn't see that. 1.5 minus 1.3, so it should be 0.2. That's it, right? Is that clear?
It says 0.20, right? You said.
Yeah, 20. Sorry. All right. Is it clear, everyone? Any questions now?
Sir,
Okay.
why can't we just use kinetic energy is equal to half mv square, not minus half mv square, and then we can find the change in amplitude.
You're saying you do half m omega square x naught square minus half m omega square x square? That's what you're saying?
Yes, sir, and then automatically I believe that half mv square will get cancelled on both sides.
Yeah. So why would you go
So
into
it
that?
will be x naught square minus x square, and then we can find it using 1.5 square
Okay.
minus.
Right. I agree what you're saying. But I'm saying if you want to go from A to B, you go directly. Why do you want to go like this? You could simply use this. Do you understand?
Yes, sir.
So no matter what, this point will always be total energy. So if you reduce total energy, the whole graph is going to be reduced like that. Do you understand this? So instead of going
So,
through
sir,
that,
if total energy is 2.4 joules, why aren't we writing 2.4 millijoules is equal to half mv square?
it is the same. It is the same. What I'm saying is the total energy stays the same throughout. You understand? Like that. So whether you take potential energy or kinetic energy, the total energy would be the same for both of them. Do you understand?
Yes, sir.
So we are taking it here because we know exactly where the total energy might be, right?
Yes,
And
sir.
this would just stay constant, and that's why we're doing this. We don't want to go into this equation because then it would take so much longer to solve, right? And we do not have time for 3 marks, right? Is that clear?
Yes, sir, I do.
Okay. Now, same question. It is 2 times maximum speed. I'm going to leave you for you as homework, but right now I'm just going to explain this. What graph is this? Potential energy, kinetic energy, or total energy?
Potential energy.
Potential energy.
Potential energy, right? So if I want to find the total energy, so what will I see? Which point?
The maximum point
Yeah,
at
this
the
one.
end.
This means it has 25 millijoules, right?
Yes, sir.
Now it says on the axis kinetic energy. How would you draw kinetic energy? You will basically start from this
1.5, then we go to
Yeah.
25, then
like
come
this,
back to
right?
1.
Do you agree? Like this. Okay. And then the next question is where you want to find the energy when it is reduced by 60. So this is very simple, the same type of question that we've just done. So I believe you guys can do this. Anyway. So again, the same thing. Also homework. Please work it out. It's very simple. Um, could you okay. It says determine the distance d through which the mass was displaced initially. Can you find it from the graph? What would be the mass? Like what would be the displacement? What do you guys say? So if you displace it, it basically covers amplitude, right? And we go up then. So can you find the amplitude here? It would be this much, no?
So 0.75, I think.
Yeah, very simple. And then show the frequency
So
as
can you
4.
please repeat that?
I think it says he like pushes it down like this, okay, from the equilibrium, and then release it. So it's going down, up, down, up. So this half is amplitude, no?
Okay.
Amplitude is the maximum displacement. So can you find the maximum displacement right here from the
Oh,
graph?
okay.
Then say show the frequency. How do you show the frequency? It's very simple. You have the mass, right? You have the mass here. You have the total
Yes, sir.
displacement, you have the total energy. So the total energy value can be seen from the graph, half m omega square x naught. You have x naught right here. You have m, you have half, you have total energy. Can you find omega? Yes, do you
So
guys
why is it
understand?
6 marks?
Because you have to take one read off from here. You have to include this reading from here. You need to include this reading from here. You need to basically apply the right formula and find the answer. That's why. How easy it is, right? And 6 marks. Imagine.
So
Arslan, do you
6
understand
marks.
this? Javaria,
Yes, sir.
you understand
Yeah, I
what I'm
got
saying?
it.
Yes, I do.
So see, sometimes the examiner is generous. So he could be a nice guy.
So are you sure there's nothing else with that?
No.
No, because sir, I'm kind of doubtful. Maybe there's something we missed.
Okay,
6
let's
months.
Yes,
should I
because
do
it's
it?
6 marks. They won't give it easily.
Okay, so let's do it then. Why do you guys worry about it? So first of all, let's find it. This is actually in the middle, I believe, right? Or is it? I don't know. I don't think so. It is in the middle. If so this is like, I hate them doing this with me. Every time they give you like a value. This is 0, right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So this is 0.5. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is 0.75, right? And this will be 0.8, 0.9. No, I don't think so, right? This is,
So
can
it
you
is
do
0.8.
0.76.
it
It
is
is
0.8?
0.8, yeah.
0.8. This will be 0.85, 0.9, 0.95. Okay, so this is 0.8, right? You guys agree? Centimeters. So 0.80 centimeters. Now, half m omega square x naught square is the total energy. The total energy is what that might be.
So
1, 2, 3, 4,
2.55, I think.
5, 6, 7, 8, 9, 10. So this is about, what's that? 2.5. This is going to be 2.6. 7, 8, 9. Okay, 2.6 and half is 2.55. You're right. Okay, almost done. So total energy is 2.55. Is was millijoules, megajoules, millijoules. Milli is 10 raised to minus 3. Half. And what you get? 130 gram. 0.130 omega square equals to 0.80 multiplied by 10 raised to minus 2. Why 10 raised to minus 2? Because we need to change it into meters. Can you please find omega? Interesting, huh? 6 mark for this. If this turns out to be all right, then I will be pretty pissed at him. For those people who might have missed it in the real exam, they would be very angry.
Sir, if the examiner is really generous in the upcoming exam, it will be really, really
Probably.
helpful.
So my
Probably.
answer is 39.6.
Are you sure about that? Did you take under root?
So it's 24.7. No, 24.8 actually.
Should I do it myself? Wait a second. Oh no, that's not fair. Frequency of oscillation. Did you change it 130? Oh my
So
goodness.
omega is 24.8, so F would be 4.
Are you sure? Can you try that, please? I thought, yeah, omega is what? 24.8.
8.
Okay, then omega is 2 pi f. So f will be 24.8. 24.8 divided by 2 pi. Can you do that?
3.95.
Yeah. So I was right about him, right? He was generous. You guys are basically not agreeing with me. That's not fair. So you see how easy some questions are? So basically what I'm saying is all this chapter you might have seen, every question is very similar. All you need to know is the right formula and you will get along with it very nicely. Okay, so this is my favorite chapter in the whole A2. Easiest one as well.
7 marks easily get taken.
Yeah, 7 marks and 8 marks easily because then he says draw a line to represent the total energy. And how do we do that? We just draw a straight line like that. How cool is that? 8 marks free, right? Although it seems like a very difficult question, but it's not. And then it says state the after many oscillation, damping reduces the total energy to 1 joules for the oscillation reduced energy. State the frequency. Would the frequency really change?
No.
No. So it will be the same, right? That's why just 1 mark. Do you guys understand? Using the graph or otherwise state the amplitude. Now for 1, what is the formula that I tell you? E1 over E2 is equal to x naught 1 x naught 1 square over x naught 2 square. So when the energy was 2.55, so x naught was, what was x naught? 0.8, right? And square. So when the energy is like 1, what would be x naught? Can you find this, please?
Zero 0.50.
0.50. Do you guys understand this? How easy it is? Will you guys be able to remember this? Let's learn this formula, please. You will be happy. All right. Now, so how many marks free? 1, 2, 3, 9, 10 free marks. Okay. Now, he wants you to draw potential energy. He wants to draw total energy. Will you be able to do it?
Yes, sir.
He has given you the mass. You can find the total energy. You can find the total displacement. Can you find the angular frequency? Omega? Okay. This is a very simple question. You guys do it. And now it says what is meant by damping, we'll do it later. Okay, damping is basically loss of energy, by the way, when it goes through a resistive force or something like that. Anyway, we are going to do this. Then it says the mass loses 20% of vibration, determine the new amplitude. So if I lose 20%, how much remaining energy would I have? 80%
80.
remaining?
Sir, 80.
So can I find the 80% remaining out of the total one? I can, right? If I use that, then how do I find the amplitude? E1 over E2 equals to x naught 1 squared, x naught 2 squared. That's it. You guys understand? Will you be able to find the amplitude? All right.
So we have to put the total energy and the maximum amplitude, I mean
Yeah.
displacement.
Yes, and 80% energy somewhere and its amplitude. That's it.
Okay.
Okay, Nadia, do you understand? Suman, Munib, Mokshit, Javeria, Gatika, Fahar,
Yes, sir.
Yeah.
Aman, Anusha? If you guys get this question wrong, because basically oscillation will be there in every paper, I would be very angry at you. So it's not something to get it wrong. Okay. Now, let me see if this is a reasonable question. Okay. So it says the ball oscillates along line AB with simple harmonic motion. So you have the frequency, you have the amplitude. Show that the total energy. Can you do that? Which formula? Please tell me. What is the formula for total energy?
Half m omega square x naught square.
X naught square. So you have the mass, you have the frequency, you can find omega, and you have x naught. Can you find it? Show it, right? Easy, right? Then it says at 2 points in the oscillation ball, its kinetic energy is equal to potential energy stored in the spring. State the magnitude displacement which this occurred. This is the question that I want to do it. So I'm not going to give you any homework for this. I'm going to solve this my own. So this is a kind of different question. Anyway, so first of all, let's look at half times 0.037 multiplied by, I changed 37 into kgs, all right? That's why I'm rating it like this. So 2 pi 3.5 whole squared would be omega squared, and 2.8 times 10 raised to minus 2 to change it into meters. Can you please do it? What'd you get?
7.0 into 10 raised to minus 3.
Which is basically 7.0 millijoules shown, right? Now, so it says 2 points in the oscillation of the ball. Its kinetic energy is equal to potential energy stored in the spring. Calculate the magnitude of displacement at which this occurs. Now, this is an important question, right? So let me just draw a graph and tell you why this is important. So we can draw kinetic energy like this. We can draw potential energy like this. Everybody agrees? He's saying at some displacement, which is this displacement, both kinetic energy and potential energy are equal.
Yes, of course, they crisscross, so yeah.
Yeah, and we want to find that. Okay. So now think about it. How would we do this? The thing is that there are 2 points, and we want to find that displacement. We know the total energy is this much, right? So total energy is given by kinetic energy plus the potential energy, and we are saying kinetic energy at that point is also equal to potential energy. Okay, right? So that means that if I say whatever the total energy is going to be, can I say if it is 7, can I say 3.5 millijoules will be kinetic and 3.5 millijoules will be potential energy then? That would basically give me a total of 7 millijoules. Do you guys agree?
Yeah.
Now, Because potential energy is given by half m omega squared x squared. So let's put it in 3.5 times 10 raised to minus 3 half. What it was the mass? 0.037 2 pi 3.5 whole square multiplied by x squared. We want to find x. Can you find x, please? Yes.
Zero point zero two.
Zero
So
point
it
zero
will
two
be
zero.
so 2.0 centimeters then. Do you guys understand?
Yeah, yeah.
Easy, right? Just a small concept. That at this point, these will be equal and total energy will be sum of this. If you remember this, obviously you can find the middle point where they will be equal. Any questions now?
So 0.02 was in meters.
Yeah, obviously I took everything as SI, so obviously this will be in meters.
Okay.
Okay. Then says on the graph, sketch total energy, kinetic energy, potential energy. Easy, right? So what do you have? 7. 7 will be 1, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 1, 2, 3, 4, 5. This will be 7. So we're going to make a straight line like this. And then one line. What was the displacement? Total displacement was? I don't know, 2.8. 2.1, 2, 3, 4, 5, 6, 7, 8. Okay, so 2.8 and 2.8. So I'm gonna do, okay, let me use a different color. Like this and like this. Okay, please make a smooth curve, not like me. Oh crap. Okay,
So why
whatever.
is it 2.8?
Because the total displacement was 2.8. Do you understand?
Oh, right.
Okay, so you always go to the maximum. This is x naughts. Okay, and then from here till 2.8, whatever 2.8 was, where is 2.8? This point, right? So you're going to go till here. Please do not join till this point. That would be wrong. 2.8. You guys understand now? And we also need to label this. Total energy is T, kinetic energy is K, and that is P. Understood? Now, the interesting question is this one. It says, the arrangement figure 2.1 is now rotated through 90 degrees so that the line AB is vertical. Which line? Okay. Like this. Saying like this. And now it says, suggest one form of energy other than those that must be taken consideration when plotting new graphs to show energy changes in displacement. Yes. What form of energy that might be?
So gravitational potential energy?
Exactly. Gravitational potential energy. Do you guys understand? Because now it's also going to work against gravity, no? All right. Anusha, do you understand for her? Arsalan, Aman, Nadia?
Yes, sir.
Excellent. Wow. All right.
Yes,
Okay.
sir.
Good. All right. Now let's move to resonance. So resonance is a very simple phenomena. Okay. Resonance has 2 points. So basically, it will be asked for 2 points. First point of resonance is that it is where or phenomena that happens when external driver frequency matches natural frequency of an object. All right, is that clear? The other thing that you got to write, that this causes the net, this word is highly important, net amplitude to be maximized. All right, so these are like two things that you need to remember. Writing net is a keyword. If you fail to write it, you get no credit for this. Now, there could be two types of graph. Okay. One graph is where there is no energy, right? This is without loss of energy, which is practically not possible. But theoretically, we can say that if this is like frequency,
Sir, could you move a bit, please?
yes, and this is the amplitude, then where the natural frequency is, let's call this F naught, then the graph would show an unlimited rise about this point. And on the other side, it will never touch the y-axis. So here, you need to remember, does not touch x-axis. Because at any frequency, there will be vibration, right? But this way, this I made a bit wrong. So this should be starting from 0. And why it touches 0? Because at 0 frequency, obviously amplitude has to be 0. Is that clear, everyone? But in reality, where there's some loss, so with loss of energy, if this is the natural frequency, this is the driver frequency, obviously, in hertz. So then, obviously, where the natural frequency is, it will create a peak like this. So peak formed at F naught. Is that clear, everyone? Rest, sorry, rest of things remain the same. Okay. Okay. Do you guys understand this? All right. Now, what exactly is a natural frequency? Natural frequency is basically a frequency of a system. You can write a system or a body at which it oscillates without any interference from external forces. So everything in the world has a natural frequency that it's oscillating with, and it's basically depends on certain things. What does it depend on? It depends on basically 4 different things. Okay. Number 1, it depends on the dimensions. With dimensions, I mean length, width, thickness, right? Then depends on the density. Then it depends on the internal structure. Internal structure means that whether it's bonded like ionically or it's what other bonding is covalent bonding, right? So it depends on what kind of bonding is there. And then physical structure. Physical structure basically means what kind of shape it is, right? So it's a round object, it's a oblique or something like obnoxiously bad looking or good looking, whatever. Do you understand? All right. If you guys have any questions, please let me know. Okay. Now, so for example, in this question, it says two vertical springs, each having constant case holds a mass, a lower spring in oscillation, right? So they've given you this equation. And now they say show that for mass 240, the springs with spring constant this, the frequency of vibration of mass is approximately 8, right? So first of all, if you look at this equation, right, this doesn't seem right. So there is acceleration here. I would like to separate it. So it will be 2kx over m times x. Can I write it like this, please? If I do that, the next logical step is to compare a equals to minus omega squared x. So omega squared will be equal to 2k over m. Do you agree? So 2 times the spring constant. Look at the spring constant, Newton per centimeter. And the mass is in 240. Should we change it? Yes, we must change it. You know why? Because the issue is that they want us to find it in hertz, right? And we should change it. Now, how do we change this value into meters? So you see, it's 3 Newton per centimeter. If I want to change centimeter into meter, what do I write? Can I write it as 10 raised to minus 2 meters, please? So then,
So it's 3 or 30?
So
Three.
it's 3, right?
Yeah. So can I write it as 300 Newton per meter then? What do you guys say? Do you agree? Now, put it here. 300 divide by. You ought to change this as well. 0.240 in kilograms and take under root. And then equate to 2 pi f. Can you find frequency, please? That's why this is 4 mark.
7.96 hertz.
Okay, so 8.0 hertz, right? Proved. Do you guys understand this? Now, they've given you this. And they say, okay, shows that the variation of amplitude is this. Now they say, state the name of phenomena illustrated. What phenomenon is this? Who's going to tell me? You
Resonance.
know this? Okay, resonance. Very good. Should be confident about it. What is the natural frequency? The frequency f naught at which the maximum amplitude occurs. And that is, who's going to tell me? The same at which it is naturally vibrating. Do you understand? At this point. Understood? Okay. Now it says, suggest and explain how apparatus could be modified to make the peak flatter without significantly changing the f naught at which the peak occurs, right? It's saying, how could we make it flatter, like less resonance? So in this one, so we don't want significantly the peak to change. Let me see where I should have basically told you about the other things. Let me see. Okay. Oh, I know. You guys are going to get a bit. Okay, we're going to come back to this question. Hold on here. I'm going to tell you. First, let's talk about damping and then come back to it, okay? So damping, I don't know why it's up, but I'm going to write it. Damping is the loss of total energy of system due to other resistive forces, okay? So it could be gradual loss, it could be like that. I just want to tell you that there are certain types of damping that we need to
So
learn.
could you repeat the definition again? I didn't complete it.
It's basically loss of total energy of system due to other resistive forces, okay? When you add some,
Okay.
usually it's 1 or 2 marks, it's fine. Written, should I go forward? Okay. Now PDF yet?
No, I don't.
Okay, that's not good. Why didn't you say so? Hassan, could you just quickly go and join the Google Classroom, please? This is the code, please. All right.
Can you send me on my WhatsApp?
Okay, that is going to be a difficult job right now.
Okay, but I'll just copy the code. It's not a big deal.
Yeah, just copy the code and then you can complete the PDF later on. Don't worry. Anyway, you'll find I'll explain it to you and at the end of the class. Let me just complete this. So now let's try and okay. Okay, going down, going down, going down. This chapter is too long, right? It's like, I don't know how many pages this was. 60 pages, right? This PDF?
60, sir.
Oh my
60.
God. Okay. All right. So now I would like to explain some of the types of damping. First of all, when there's no damping, right? So what happens is that the wave doesn't lose amplitude because it will basically have no damping. And when there's no damping, we say it's naturally oscillating. Do you understand? Naturally oscillating, some people like to call it free oscillation because there's no external force acting. But light damping basically means that there is sort of a gradual loss of energy. We do it by attaching feathers, a little bit of air resistance, etc. Right? Like that. So gradual loss occurs when you see the wave basically slowly dying out in many oscillations. Do you guys understand this? So if you see the energy is gradually is decreasing. All right, everyone? Like that. So amplitude slowly dies down in this with respect to time, obviously, in many oscillations. But when it comes to heavy damping means then now we can write it is basically returning back to equilibrium after an exaggerated amount of time without oscillating, which means that you displace it once and now it will just cause it to go and just return after a very long time. Do you guys understand this? And it will stop oscillating. So energy loss is quick, but it's long, like it will take some time. And the reason how we do this by putting oil. Do you understand?
So is it with oscillating at the end?
Without, sorry, without oscillating. So it doesn't oscillate, but the loss of energy takes a lot of time, but it's not oscillating. Understood? Now comes critical. Critical oscillation means that basically once displaced, body returns to equilibrium in shortest possible time without oscillating, which means that it's like it will be like this. You try to oscillate it, it will just come back and die down.
Sir, you wrote once displaced, body returns to equilibrium.
Yeah, it returns to
Yeah,
equilibrium in
okay.
short possible time without oscillating. So just you displace it to some amplitude and then it will come back. It won't oscillate at all. So you're critically damping it. And how to critically damp it? You use Porter. Use something like rubber, heavy one, or shock absorbers, right? Like that. In cars, usually we use that. Air something like that. Is that clear, everyone? Okay. Now, what happens is that when you do this, so this really affects resonance because you don't want resonance all the time. Sometimes you do, sometimes you don't. Resonance has more like disadvantages than advantages. Like it's good in opera. The women sing and they break the glass, so it's a nice sight to see. But then in cars or bridges or buildings, it may cause destruction of things because the energy increases. If there's an earthquake, there's a shock, and that might, just damage the object. So we don't want that, and we want to damp it. And to damp it, basically what we're doing is, so when you draw the graph of amplitude and displacement, sorry, frequency driver. So what happens is that if it's free oscillating, obviously, like I told you, in free oscillating, it just keeps on going on like infinity until the object cannot hold it and will be broken, just like the glass we see. So it's freely oscillating object. When you give it resonance, the net amplitude keeps on increasing. Light damping causes it to have a peak, but then obviously it will have a certain peak. So it doesn't change the peak. So the peak is right here. So this is the light damping. Using it with feathers or lightly, just putting a little bit of friction or something. But heavy damping causes it to shift the peak a little bit, but it's not that, it's less than that. So if you see, the peak has been shifted here. So this is heavy. And critical damping is the most severe, which causes it to have a larger shift peak and like this. Now you might be wondering why the peak is shifting. Because the peak shift means that now the natural frequency is sort of changing, right? So we can actually ask that why peak shifts. And the reason is that when we add, when we add a damper with significant density, like in heavy or critical, we add water or oil, which has a good density, amount of density itself. It also causes the natural frequency to change. Thus, the peak shifts. Now, what I'm saying is, suppose there's an oscillating system, right? And you attach feathers to it. Would it change density of that system significantly? What do
No,
you guys say?
sir.
No, not.
So the peak stays the same, as you see, because I told you that natural frequency depends on the density, right? Now, in the same system, you put it in the chamber and you put water or oil. Would it change the temperature significantly?
Yes, sir.
So then the peak will shift. Do you guys understand this?
Yes.
All right. Okay. Right now, I just realized it's 8:10. So Namal is going to kill me. So it's better that I finish it off here, and tomorrow we'll just finish the chapter
Could you
and
read the last part of what you wrote? It also causes a natural frequency too?
change.
Yeah.
Thus the shifts.
Oh, okay, okay.
All right.